Morning, students. We have been solving we have been solving problems from the external flow case. We have seen some problems in the laminar flow. Various cases we have seen in laminar flow in the previous class. In the last class, we have seen some problems based on turbulent flow. Okay, so we have also made use of these formulas, these ones, this one, and this one also we have made use of. Okay, this one we have made use of. So this is what we have done, and let's solve few more problems today that will help us use the remaining formulas also. So let me move to our Google Doc. Right, this is our problem here. Before we go into this problem, let me ask you a question. Okay, let me take this example itself. This one itself, the previous one that we have solved in the last class. Let us look at this. If you look at this, can you tell me the point where the flow turns from the laminar to turbulent? That is, if I take a flat plate here, and if the flow is flowing in this direction, the boundary layer will be something like this. That is, till here it will be laminar. In the beginning it will be laminar. After that, the remaining part it will behave as a turbulent flow. So this we know from our fluid mechanics knowledge. Now, what I'm asking is, if you wanted to know where is this flow converting into the laminar, from the laminar to the turbulent, when the flow is converting, when is the flow converting laminar to turbulent, where is the flow is converting to laminar to turbulent. So so kindly tell me where is this point when the flow is turning laminar to turbulent. If you want to find it out, how do you find it out?
Sir, if you take RE as a critical Reynolds number and
Hmm.
find out in a reverse, like
Hmm. Get
then
REC, comma, flow turns laminar to turbulent. So at REC, the flow will turn from the laminar to the turbulent flow. So if I want to write it here, I have to write it this way. The REC is equal to V into X by nu. I have to take here. In the place of REC, what I have to put? I have to put 5 into 10 to the power of 5 I will put. And on this side, you will put the appropriate values of V into X by nu. In this, your V will be known to you, and nu you will get from the data book, and it will also be known to you. The unknown value here is the X value. Okay, this X value, if you find out, you will get the point where the flow is turning into the laminar. That is, all of you draw this figure. This is important for all of you. This is laminar, and this part is turbulent. Okay. If you want to get the value of this x here, this x is this is your x. So how do you find out x? This is the procedure for finding out this x. So that's the thing you should have in mind while solving some problems, especially this particular problem is of that kind. Right. Let's look at this problem. If you look at this problem, it is a problem based on the above problem that we have already solved. And he's asking you to determine the average convection coefficient. That is H value he is asking you to find. H bar to be precise, it is H bar because it is average. And CF value is asking. Okay, you have already found out this H bar and CF in the previous problem itself. Then why is asking again? Because he's asking in a different way now. Because he's saying that taking into consideration the laminar region, this is the key in this particular problem. These words are very important things in this problem. See, in the previous problem that we have done, what we have done is we have made use of these formula. Okay, all these formula we have made use of. All this formula will be valid when the flow is fully turbulent from the leading edge. Meaning what? If this is your flat plate and flow is like this, your boundary layer is like this, and from here itself it is turbulent. So from the leading edge it is turbulent, you will use this. Okay, if the given flow is of this kind, you will use this particular thing. But in some cases the flow will be laminar in the beginning and turbulent towards the end. So to consider this effect, what we have to do, you have to make use of this laminar turbulent combined formulas. Laminar turbulent combined formulas. Laminar turbulent, considering the laminar length. These are the formulas that you are having. Okay, so kindly note this. If the laminar length has to be considered in the given flow, you have to make use of these formulas. So let us solve this problem based on this laminar region, considering this laminar region also. So how do you find out this laminar region? Just now we have seen REC is equal to V into X by nu we have. The REC value is 5 into 10 to the power of 5, and the V value is given as 4 meters per second in the question. So let us substitute that 4. See here, what is the value of X? What is the value of X here?
We should
This
find
x value is unknown. You are actually finding it out. So you have to get that x value. What is the new value? New value is given in the question here. It is 1.006 into 10 to the power of minus 6. 1.006 into 10 to the power of minus 6. Tell me what is this x value? Yes. Tell me what is this x value?
1.25, sir.
It is 1.25 meter. Huh? In 1 meter, if it is 1.25 meter, the whole length is laminar itself. I don't think it is correct.
0.125.
75, sir.
Yeah, it is. It is 0.125 meter. See, this
7.
whole length. Yes, somebody is asking any question. This whole length is 1 meter as given in question. Is 1 meter. The laminar length is 0.125 meter. The remaining length, that is 1 minus 0.125, is turbulent. That's the meaning of this is laminar. Okay. So, is that clear to you? Somebody please respond. Is that clear?
Yes, sir.
Right. So that's how you will get the x value for xc. Strictly speaking, this is xc. Okay, let me call this as xc. Now, what you have to do is you have to find the value of the h bar and cf when you have the laminar and turbulent flow. So you have to choose the appropriate formula. So let us find out this delta x first. This delta x formula, let us write delta hx is equal to 0.381 into the x into re power 0.2 minus 10256 into x into rex power minus 1 0. Okay, this is your delta hx value. In this, which x will you use? What is the value of this x? What is this rex? Tell me. What is this x equal to? Please tell me. Somebody, please tell me. What? This x
X equal
is 1 meter. Okay. In this formula, this x is the whole length that you are considering that you are flow is flowing. So that x you have to consider. And rex, if you calculate it, will be like v into L by into x is more proper way of showing it. V into x by nu. The v value is 4, the x value is 1, and the new value is 1.006 into 10 to the power of minus 6 given in question. So tell me what is this value of rex? And you have to substitute these values into your delta hx. So the delta hx is equal to 0.381 into 1 into rex. What is this rex value? This value, what is this value? This one.
39761
3976143.141. So what is the meaning of this? It is in its entire length, it is a turbulent because it is greater than 5 lakh. Anyways, 3976143.141 whole to the power of minus 0.2 minus 10256 into 1 into the Reynolds number 3976143.141 whole to the power of minus 1. So tell me what is delta hx value now?
0.01566.
0.015
Double six.
double six 015
Yes, sir.
meter. Okay, delta H is 0.0. Or higher. Let us keep this aside and let us move to the calculation of the CFL. The CFL, let us find out. Let's make use of this formula here. Let me write it. CFL is equal to 0.074 into REL power zero point 0.2 minus 1742 into REL power minus 1. Okay, so this is equal to 0.074 into the REL is 3976 143.141 whole to the power of 0.2 minus 1742 into 3976,143.141 whole to the power of minus 1. The CFL value you calculate and tell me.
0.0031.
That's the CFL value. You keep it aside. Let's move to the calculation of the Nusselt number now. Nusselt number calculation. Let's do the Nusselt number. NUL bar is equal to the Prandtl power 0.333 into 0.037 into REL power 0.8 minus 871. This is your Nusselt number. What is the Prandtl value? The Prandtl value is given in the question here. See, even if it is not given in the question, how to take it from the data book. Okay, it is 7.02 given here. 7.02 whole to the power of 0.333 into 0.037 into 3976,143.141 whole to the power of 0.8 minus 871. Tell me what is this NUL bar value?
To 11810.59. Eight
Repeat.
one zero.
0.5. Am I right, Harish?
810, sir. 11810.
1.
11810.
Okay, let me correct this. Am I right now?
Nice. 0.6.
0.6. Right. Let's keep this one also aside. Using this, let's calculate the H bar now. The H bar into the L by K is equal to 11810.6. So this will imply the H bar into the L value is 1. The K value is given in the question. Basically, you have to get it from the data book. In this question, he has given it to you in the question itself. 0.59, what is it? 5978 has given, is equal to 11810.6. From this, tell me what is H bar.
7060.37. 60.37.
7060.37 watt per meter square Kelvin. This is your H bar value. Now, what we will do, we will compare the values that we have got in the previous problem. So in the previous problem, we have done for delta Hx. What is that? Fully turbulent. Delta Hx, what is the value? Move to the previous problem and you will find it. Tell me what is that value?
0.018
0.01824 meters. Can you find out the difference? See, if it is fully turbulent, the delta Hx is bit more. Okay, so that's the difference. Likewise, you tell me for fully turbulent CFL
0.0035.
0.0035. Even this friction coefficient is bit higher in fully turbulent case. Coming to the Nusselt number average, NU bar. Did you do that?
13398.68.
Good. 133.6.
Itself 98, sir. 13398.
13398.6.
Yes, sir.
Right. That is NU bar. So even the NU bar is higher in fully turbulent case. Fully turbulent case. What is the H bar value?
8009.73.
8009.73 watt per meter square Kelvin. So what you can observe is in fully turbulent case, generally the values are bit higher. Okay, all the values are bit higher. So if you are considering it to be fully turbulent, the estimation is bit higher compared to the actual thing. So if you consider the laminar turbulent formulas properly here, that will be of more use. Okay, fine. Let's move to the next problem. This is an air problem. Let us do this quickly. First thing to do is to know the kind of material used here. Air is used here, and it is flows over a flat plate. So it is an external flow over a flat plate. External flow over a flat plate. And the next thing is to find out the TF. So to find out TF, you should have T wall and T infinity with you. So it is given that T infinity is minus 10 degrees centigrade and T wall is given as 0 degrees centigrade. So what you get here, it is 10 minus 10 by 2, which is equal to 0 degrees centigrade. So all the properties are to be evaluated at 0 degrees centigrade. Okay, that's the thing. And what else is given? Velocity is given as 10 meters per second. The velocity is 10 meters per second, and the length is given as 3.1 meter here. Determine the average value of friction coefficient, convection coefficient, taking into the laminar length. This is very important. This is very important. Taking into the account the laminar length. So we should consider the laminar values, and he's also asking you to compare those with the assuming to be fully turbulent. So both the things you have to do. Okay, with the laminar you have to do, fully turbulent you have to do. So that's the question. In two cases, you have to find out the value of friction coefficient and the convection coefficient. Friction coefficient means what? CF, and convection coefficient means what? H bar. Okay, so these are the things you have to find out in both the cases. Okay, let's do it quickly. The first thing to do here is to find out what laminar length here. Laminar length you have to find out. Sorry, I must leave some space here to write all that properties. Okay, let me leave it like that. So to find out whether it is laminar or turbulent, what I have to do? We have to do the Reynolds number calculation. Obviously, it will be turbulent because he is saying that considering laminar in the question, obviously it will be turbulent only. V into L by mu we have to do. V is given as 10 meters in question. L is given as 3.1. Nu is unknown to you. You have to get it from the data book. Go to your data book. Move to the page number of air. It is page number 42. Move to page number 42.
Sir, is it 0.6 meters?
I don't write. For 0 degrees, you take new value, this one, 13.28 into 10 to the power of minus 6. This is 13.28 into 10 to the power of minus 6. New value is 13.02 into 10 to the power of minus 6 meters square per second. So tell me, what is the Reynolds number value now?
233 4 3 3 7.
233 4 6 6 1.
Not
Is
no
it
sir.
right?
No sir. 4337.
Am I right now?
Sir. 0.34.
Point
33.
0.3. So RE value is greater than 5 lakhs. What does that imply? The flow is turbulent. Okay. Laminar length. Laminar length you have to find out, and the laminar length will be like RE is equal to REC is equal to V into XC by nu. So what it will be like? It will be 5 into 10 to the power of 5 is equal to the V is 10 meters per second. XC is unknown, and the new value is 13.28 into 10 to the power of minus 6. Tell me, what is this XC value fast?
0.664.
0.664 meters. So what does it imply? In the entire length of, what is the entire length of what? What is this entire length? It is 3.1 meters. In 3.1 meters, your 0.664 in the beginning is laminar. The remaining, that is 3.1 minus 0.664 is turbulent. That's the meaning of it. So what he is saying is, he want you to do it this way, do the calculations this way. On the other side, he is also asking you to do the calculations by considering that the whole length is turbulent. Okay, the whole thing is turbulent. So what you have to do, you have to get the H value and CF value in both the cases. Okay. So let us do it in the laminar and turbulent case in the beginning. For that, what you have to do, you have to take the CFL formula. Where is that CFL formula? It is in page number 123. Page number 123, you have this formula. It is CFL is equal to 0.074 into REL whole to the power of 0 point minus 0.2. Minus is very important. 1742 into REL or minus 1.0. So that is equal to 0.074 into the REL value is something that you have found out just now. What is that? It is 233 433 7.35. 233 433 7.35 whole to the power of 0.2 minus 1742 into 233 433 whole to the power of minus 1. So tell me what is the CFL value?
0.0031.
0.0031. Okay, this is your CFL value if it is laminar turbulent. Now, if it is turbulent throughout, if it is turbulent throughout, what is the formula that you're going to make use? Here, if it is fully turbulent, the CFL formula is here for you. Okay, can you see that? Let me change the color, more visible. Here it is. Okay, I will write this one here. This is equal to 0.0592 into REX power 0.2. Here it is. This one I have written. Right. So quickly do this calculation. 0.0592 into 233,433,7.35 or to the power of 0. Minus 2 minus 0.2. Anyways, what is the CFL?
0.0005.
0.005.
5.
315.
315. Is that correct? Somebody please
Yes, sir.
confirm it.
Yes, sir. Yes.
Yes, sir.
Right. CF in both the cases, you are done. And what is the next thing to do? You have to find out the H value. For finding out the H value, you have to find out the NU value. For finding out the NU bar, what is the formula in laminar turbulent case? In laminar turbulent case, the formula is this one. So let me write this formula here. This is equal to Prandtl power 0.333 into 0.037 into REL power 0.8 minus 871. 871. This is the formula. What is the Prandtl value? You don't know. You have to get it from the data book. So move to the data book, to the properties of air, get the value of the Prandtl number at 0 degrees centigrade. It is 0.707. The Prandtl value is the Prandtl value is 0.707. Substitute that Prandtl value here, 0.707 whole to the power of 0.333. into 0.037 into the RE value is 233 233,433,7.35 power 0.8 minus 871. Tell me what is this NU bar value?
Double three double 2.14.
Double three double 2.14 is your Nusselt number value. Okay, you're done with your NU bar. What you need is H bar actually. So H bar into L by K is equal to double three double 2.14. The L value, so the H bar into the L value. What is the L value in this question? It is 3.1 by the K value. You have to get it from the data book. So in your data book, the K value is 0.02442. 0.02442. 0.202. That is your K value 0.2442. Double three double 2.14. H bar is equal to
26.17.
26.17.
7, sir.
Okay. So this NU bar and your H bar you got in the case of the laminar turbulent combination. Now let us do it if it is fully turbulent. This is for combination of laminar turbulent. So, so now you have to do it for fully turbulent. If it is fully turbulent, what is the formula for NU bar? You go to the fully turbulent formulas. It is here fully turbulent. In this, what is NU bar formula? This is your NU bar formula. So write that NU bar formula here. NU bar is equal to 0.037 into RE power 0.8 into the Prandtl power 0.33. So, Reynolds and Prandtl, simply substitute them here. 0.037. The Reynolds is 7.35 whole to the power of 0.8 and the Prandtl is 0.707 power 0.33. So tell me what is this NUL bar value?
4102.42.
41
02.42.
0.42. That is NUL bar value. What we need is H bar. H bar into L by K is equal to 4102.42. So the H bar into the L value is 3.1 given in question and the K value is 0.02. What is that? 0.2442. 442. is equal to 4102.42, and the H bar value you tell me.
32.31.
32.31 watt per meter square Kelvin. This is your H bar value. So he has asked you to compare both the things. So for comparing, you put out a table here. So let me draw the table here. Firstly, laminar turbulent combination on this side. On the other side, fully turbulent. See, whenever in question, if he's asking you to compare, no, you draw the table. The comparison will be clear to the evaluator. Okay, he need not search for comparisons in your uh, answer script. Okay, I remind you once more time that the evaluators will be not very active. They'll be a bit lazy, so you have to understand that. So first thing what we have found out here is CFL. CFL. Next thing NU bar. Next thing H bar. Tell me what is the CFL initially?
0.00319.
This one 0.00319. 0.00319. The other side 0.00315. NU bar 3322.14. NU bar on the other side 4102.42. H bar on this side 26.17. It's 32.31 watt per meter square. So this is your comparison. Okay. In this comparison, can you learn anything here? See, if the laminar turbulent flow is considered, the H value is very less compared to the fully turbulent case. So if you keep on increasing the H value, that will be not correct value, correct estimation of your H value. If your H estimation is missing, your Q estimation also will miss. Okay, ultimately, why do you want to find out the H? Because Q is equal to H into A into the Q is equal to H into A into the delta T. So what is the use of finding H? Ultimately, you want to find out the Q value. So if your Q value will be higher if the H value is higher. So ultimately, your Q is not estimated properly. So that's what the disadvantage of you know fully turbulent case. So it's always suggested that you use laminar turbulent case in a given problem. First, you find out the laminar region, whether it is a laminar or turbulent. Based on laminar region, you will choose the appropriate formula. So, with this, I would like to conclude the flow over a flat plate. Okay. So let me quickly review what we have seen so far. See, this is the external flow problem we have seen. And in this flat plate, we have two cases. One is a laminar. We have seen some cases in laminar. The other cases which we have not seen, you check for yourself. This we have not seen. So you check for yourself. Likewise, this one also. Okay, kind of this is solved. for constant temperature case here. So the other one, you check it for yourself. And in the turbulent, we have solved fully turbulent and laminar turbulent cases till now. And in the flat plate, the constant heat flux case also, you do it. Okay, it's like constant wall temperature only, but only 1.04 times it varies. Do it for yourself. And this is analogy. Okay, this is a Stanton number. ST means standard number. Okay, so this I will tell you in future. Don't worry about that. So that one and this high speed flow case also you do it for yourself. So that's all. So with that I complete external flow in flat plate. In the next class, let's move to the external flow over a cylinder. Okay, flow over a cylinder. Let's start in the next class. So that's all for today.